Thank you for coming. I think there will be more people coming in. Dr. Benny Varghese we were very fortunate that Dr. Varghese was in the vicinity in DC at this time. So we were able to poach him and bring him in person to speak about a hot topic of cybersecurity when it comes to electric vehicles. We had a good fortune to work with Dr. Varghese's group a couple of years now, and I'll let him introduce himself and talk about things that we've done or maybe some other things as well. But we're really fortunate to have Benny here. So enjoy and please ask questions. Dr. Varghese is a very easygoing, very knowledgeable, and knows what's going on in the industry in US and around the world. So Benny, take it away.
Thank you, Miloš, for that introduction. So good morning, good afternoon, everyone. I'll try and get a quick survey feel for the room. So is everyone here grad students or are there undergrads? Do we have professors other than you, Doctor? Okay, all right. Okay, awesome. Let's see. So today's talk, I kind of titled it the cyber physical security for electric vehicles and electric vehicle charging infrastructure. But if you came into this talk hoping to learn how you're going to hack an electric vehicle, you're going to be disappointed because I don't know anything about that. So what I'm going to give you is a little bit of perspective on the electric vehicle side of things, like how that hardware works, what things are connected, what is connected to each other. And that hopefully should give you a feeling for what kind of projects you want to work on, what is possible in the field. And this is just meant to inspire you in terms of ideas, what you can do in the future, what you can get into in this space. So before I get into talking about the lab, so my background is in electrical engineering. So I got my PhD from Utah State University, worked on power electronics. So I developed some wireless, wired, conductive, high power charging systems for electric vehicles. So that's where I got my start in. And then I moved on to the Idaho National Lab, where I currently work. So the lab itself, we are in Idaho. I hope some of you have heard of the place at least. So that's far northwest in the US. The lab itself, so we work somewhere about there. But this, the picture here is of the nuclear engineering research site. So large area, lots of test beds, lots of different fields of research going on. And then the next one we'll talk about is our Integrated Energy Systems Laboratory. So that's our picture. That's a picture of our Integrated Energy Systems Laboratory. But the electric vehicle portion itself is just in that corner. So we work in this area over there. In the far corner here, we have some grid research, RTDS systems, and the whole of the central area is hydrogen-related research. So a little bit of overview of what we have in our electric vehicle infrastructure lab, or EVIL for short. That name you'll remember. So we have hardware evaluation and characterization capabilities. We've got some wireless power transfer test beds. We've got conductive charging system test beds. We've got level 1, level 2, DC fast, extreme fast charging. So sure, you've probably not heard of those terms before, but all that tells you is what power level you'll be charging your electric vehicles at. So all the way from 1 kilowatt to 350, 400 kilowatts plus. And a little bit more on the cyber physical security research. We'll get into that briefly. We look at vulnerability and assessments, impact severity, cyber manipulation complexity, mitigation, et cetera. And lastly, we also look at grid integration. So what happens when you add a bunch of electric vehicles to the grid? So is that going to support it? That sort of analysis. Where do you need to put your chargers? Is there enough power in that area to support the chargers, and so on. So as you can see, it is a pretty broad area of research, but there is the one tying point together is energy and transportation. A few more pictures. So that's what a charger looks like. So again, before I get into that, how many of you have driven an electric vehicle before? Show of hands. Just one? Okay. We'll get you more interested by the end of this. So that's what a charger looks like, a public charger. So this is what we would typically call an extreme fast charger. Again, these terms are applicable today because today that is extreme fast charging. Maybe 5 years from now, that would be normal charging. So this is what it looks like. So 350 kilowatts, what that means is you can charge your vehicle in about 15 to 30 minutes when you just pull in. It's the equivalent of getting a full tank of gas in your vehicle. And we also have an electric bus that takes employees out from the town to the nuclear site in the desert. So that one is also, we run some tests on that with the same charger. Didn't quite have enough space to bring the whole bus in, so we just had to open the door, just back it up. And then again, in the corner here is a smaller version. I would just say earlier version. So if you see that tower over there is about the same size as whatever was there. Yeah, right there. So here, this was a 50 kilowatt charger and this was state of the art 4 years ago, 5 years ago sometime. So we've been working in this space for a long time. And so now we're moved on to like the latest and greatest at this point. So quick refresher on resilience and reliability. So we want to talk about, so the axes that are on this figure is one is the magnitude of the event or the impact of the event. And we've got the probability of that situation happening. So reliability primarily deals with the high probability events that are expected over the lifetime. For instance, you're talking about temperature cycling, you're talking about somebody driving into your charger, backing into your charger or whatnot. So that is all high probability events expected to happen within the design life. That's what you design for. It's called reliability assessments over there. And rest of this, where it's like higher magnitude events but lower probability, is extreme events that can be anticipated, probably some kind of flooding, some kind of extreme weather conditions, et cetera. And far away there, you've got even like black swan events, kind of cyber attacks on the grid itself, taking down the entire network and so on. So we play in this entire space. So we do deal with the reliability side of chargers and also a little more research going into the resilience and risk areas of that chart too. So one event, I wasn't planning on talking more about this, but I will give you a quick snapshot of this. So this is what we call the ChargeX Consortium. It's a new effort from the Joint Office of Energy and Transportation to improve the charging experience. So if you've had electric vehicles or been following that space for any amount of time, you're probably familiar with the amount of problems that exist in the charging space. So you'll see news articles about chargers broken, did not work. It's not worth getting an electric vehicle. So that kind of inspired this effort of getting together some national labs and some industry groups together to make sure your charging works as expected when you need it. So the idea there is any driver, any method of authentication, whatever charger, whatever vehicle, different protocols they're using, it should work as expected the first time, every time. So I'll skip over. It gets into a little more detail on what the exact consortium is trying to do. So what we want to do here and how this is relevant for you. So if I understand correctly, most of you are computer science, data science in that field. So we talk about understanding customer pain points. So well, I'll show you some slides on that real quick. So we'll come back to that. Then the other is to develop meaningful KPIs. So like we say in engineering, so if we want to improve something, we need to be able to measure it. And so developing that data-driven approach of how we want to understand what exactly the state of charging is currently and how we improve it going forward. And the last few are more on the hardware side of things, diagnostics, root cause analysis, interoperability, scaling, et cetera. Okay, getting back to the customer pain point analysis. So this is a little more on the data science side of things, where we wanted to first understand where customers are facing problems with their electric vehicles. So for this particular analysis, this was a project that we ran, I think, mid last year sometime, where we just took a bunch of data that we took from publicly available reviews or posts on social media where we look at what kind of problems are they talking about. So you'll see on charging apps, somebody will say, hey, charger was broken or cable was broken. I was not able to get a charge. Or somebody that says, hey, great experience. It charged first time I plugged it in. So taking all these different textual data, running it through our machine learning algorithms and trying to classify them into the right categories, all of that running through, then that gives you a wide range of data to play with. Now you can look at when are these negative reviews coming in? Is it in a particular season? Is it during the holiday weekend when everyone's traveling, trying to get a charge, and so on. You could talk about which geographic locations are you having more problems with. Obviously, if you have more chargers, you're going to have more problems in that area, but also trying to normalize that with the number of chargers in there and so on. So a snapshot of initial results that we got from this work. You can rank a list of problems saying, had to try multiple chargers. I went to the station, plugged in, did not work. Had to move around to the next charger, try multiple times to get there. Second most common one is did not get a charge at all. So they either went to a different station or just went home if they had enough juice to go home. And lower power than expected, and so on. Well, we can skip through the rest of those. And like I mentioned, you can break it down by months, by seasons. You can look at when do you see the most amount of events going on. Again, this by itself is not you cannot justify data just like this. So you have to overlap this with the rollout of chargers, right? This graph, first thought you get from looking at this is, oh, the problems have been increasing, but that's not necessarily true, because this was also the time when you had a lot of chargers being deployed. So you have to, again, look at how you want to normalize that, make sure that it is under the same conditions and constraints for the entire time period. And that's when you can get some good insights into it. Yes?
You think weather had anything to do with it either?
Yes, I'll get to that real quick. So winter typically has had more issues, especially the last couple of years. And I'll talk a little bit more on what that looks like, some causes and tips for you too, if you want to get an EV and are going to struggle in the winter. I talked a little bit about KPIs, and what that looks like is what does first-time plug-in success look like? What is the availability? Mean time between failure, mean time to repair. This is all from industrial engineering. The other kinds of data we can look at. So again, what we have on the screen here is just an exploded view of all the different subsystems that go into an electric vehicle charger. So this orange box right here is the electric vehicle itself. So you've got the vehicle controls, vehicle internal components there, the battery pack, and the DC connector. The connector being the port where you plug your vehicle in. And on the charger side, you'll see the word EVSE, which stands for Electric Vehicle Supply Equipment. Throughout this presentation, if you see that anywhere, I'm just talking about that giant post that I showed you in the first few slides. And so that is typically what you have inside an EVSE, and at the end, it is another DC connector that plugs in here. And you've got cable cooling, coolant pump, and so on and whatnot. So with root cause analysis, what you're trying to get at is take all the data of so many charge sessions that you have on hand, try and look through where things have failed, what kind of things have failed, and then you're able to assign probabilities for different parts that get an idea of what's going to fail next, or what are the parts that are causing the most issues, and then you focus your attention to those problems, because you fix those, you solve a majority of the problems. I don't know if you've seen this image in the news at some point. This was mid last year sometime. We've got some hardware issues here. There was like a little fire that kind of blew up a bunch of things on the vehicle charger. Again, not to scare you from electric vehicles, but that is the reality of what happened at that point. So if you see, that's sort of what the connector looks like. To explain what happened here, you need to understand that some of this. These two pins over here are the power pins. So we've got, this is where the DC power goes into the vehicle. Everything up here is what's called the control pins. If you notice, you'll see that these are a little more recessed back in, and these are longer. So the idea behind that design was, if you think about these being the control pins, and you're trying to unplug, you want the control connection to break first. So as soon as the control connection breaks, the power gets killed. So you don't have power when the actual high voltage line is being disconnected, right? So that's the idea. So you want to make sure that no matter how you pull it, the control circuit breaks first, and then you leave the power circuit. But what was happening was what happens when you take this, and now the car is lower, the port is lower, and you're pulling it upwards, right? Now your C goes that way. So your control connection is still established while you're trying to break the power connection. And that itself doesn't cause an issue. And so, which is why you can't really identify it. But over time, you'll start noticing that every time someone does that, there's a little micro damage that happens on this part, not from mechanical forces, but just arcing. So it's just a small arc every time, slowly degrading the plastic enclosure and so on. And then one fine day, unlucky customer ends up like that.
But let me ask you this, is it because you being used to regular gas station that has that curve,
Yeah.
typically take it this way, but people that start with the electric vehicle, they don't have that habit.
Yep.
They will start getting this, right?
Yep. So yeah, again, you can see how many different things play into it. One, weight of the cable. Customers are not used to the amount of tension that is on the cable itself. And then you talk about different cable design, different user behavior, and so on. So, and that issue has been fixed. It's been dealt with. So don't take that as your main takeaway from today's presentation. All right, diagnostics and testing. So I talked a little bit about diagnostics, understanding what these failures are, how these can occur, and then that gives you insight into what you need to be looking for. As an engineer that is in charge of dealing with the reliability for chargers, then you get some data that helps you understand what kind of errors you should be looking for, what you need to be, what issues you need to be maintaining for. So if I know an issue like that has been happening, I know I can send in a maintenance person to go take a look at that every so often, and that decision-making is facilitated by the data that you have. So this again is a little more detail on this slide. I'll talk you through it real quick. This is to show you all the different communication protocols that exist in the EV charging ecosystem. So let's talk about from the EVSE again. So in a charging station, you've got several EVSEs, right? That's what you would see in a typical charging station. And the EV to EV EVSE is pretty standard communication, and then back from EVs, different EVs send data back to your vehicle manufacturer. So if I've got a Ford Lightning, my vehicle is sending data back to Ford, and that's just diagnostics data. And that is not unique to EVs. That happens with any new vehicle. I think over 2014, 2015, that's when it started out. So everything that's in a dotted line is a proprietary form of communication, as in it varies from, not proprietary, but it is not non-standard mode of communication. Everything that is solid has a name to it: OCPP, OCPI, OICP. For some reason, all the players in the field like to use O's and C's and P's in different arrangements. So they're all different standards. You've got OICP, OCPI, whatnot. It doesn't matter what they are right now, but just to give you a snapshot of all the different links. And why is this important? Because as a cyber person, if you're looking at securing these, you need to just understand what each protocol does and where is that communication. So if you were to read that particular link, right, that tells you all the diagnostic data, charging information, and user information going from the EV to EVSE and to the back office. This is all what you would think of as back office, the network that actually facilitates the transaction for the charging station. So again, this is just to give you an idea of the amount of network links that are present, just to give you a feel for that. So summary of our reliability efforts, we work a lot on that, is one, we've got range anxiety from electric vehicles. We just want to make sure that the charging network is reliable enough, almost to the point of the gas station model, where it's like you go to a gas station, you know it's going to work, you get your fuel, go home, or continue on your way. With EVs, it's not quite there yet. From initial studies and our own research, we found that it's about 70 to 80%. So you show up, you've got a 70 to 80% chance of getting a charge. So 20% is still pretty high, especially when you need to, when EV charging stations are not as common as gas stations just yet. So going back to a little bit more on the resilience. So we talked about resilience, and for instance, picture on there is a Tesla supercharger station that's been flooded. So obviously, at that point, you're not really making decisions based on some computer data that you got. You can clearly see on weather data, or just look outside your window, you can tell that the charger's not working. So with the resilience side of our efforts, what we want to do is we want to identify situations before they happen, or close to real time, as in when we start seeing these issues or anomalous behaviors or malicious events, etc. And also includes weather, cyber threats from bad actors, or equipment malfunction, or operator errors as well. And the image in the bottom, this is from this past week on Monday. This is a site in, can't remember where, but so what happened there was cold weather, to your question of cars weren't charging. They pulled up in there, everyone plugged in, it wasn't charging. So to understand that, you kind of need to get a little bit of background on the battery side of things as well. You probably heard, batteries don't charge as fast in cold weather, don't charge as fast when you get to closer to 100%. The best analogy I've heard for that is think of a parking lot and vehicles going into the parking lot, right? So the electrons going to the batteries are kind of similar to the vehicles going to parking lots. So if the parking lot's full, you take a long time to find your parking spot, and so fewer cars can go in at the same time. And the parking lot's empty, a ton of cars can come in, everyone can find a spot, everyone's happy. And probably extend that to just being cold as well. You've got snow and slush, everyone's driving slowly, bumping into cars, it's all slower. So one, the process is slower, and second is user behavior. Like if you're not aware of that, you probably pull into a charging station with your juice on 5% or whatever, and you're trying to charge, but the charger says, no, I can't do this. I need to heat up the battery before I can supply my full amount of power, right? And so where does that heat come from? That heat typically comes from the motor itself. So if you're driving somewhere, it's what's called preconditioning your battery. So the vehicle knows you're going to a charger, it starts using some of its existing battery to generate heat to heat up the battery pack. And from the motors as well, if you're actually driving. If you're going from home to a charger just to charge it, those are times where it uses existing power to heat up the battery. So what happens when you're really low on power? You don't have enough power to heat it up. And that's when you go to a supercharger, you expect a 200 kilowatt charge, you're only getting 2 kilowatt charge, which is slower than what you could have charged at home. So that's how you end up with that situation. Another unique problem is, I don't know if you know this, but electric vehicles also have a 12-volt battery. And you might ask why. So that runs the internal computers and so on, very similar to an internal combustion vehicle. So what happens is the larger battery, which is the drivetrain battery, actually charges a 12-volt battery in a similar way that an alternator in your gasoline vehicle charges your battery. So what happens when your 12-volt battery dies? Your 12-volt battery dies, you're stranded on the road, you think, hey, my car ran out of juice, which is why the screen's not turning on. and you get a tow truck, you get towed the 2 miles or whatever it is to the charger, you plug it in, but the charger won't respond because there is no 12 volts and there is no computer to tell it what to do. And so now you got to take that 200-mile tow to get to a service station when all you needed was a jump charge from a friend or neighbor, or just carry one of those portable chargers. So a lot of it is knowing what the system is, what the system's doing, and what you can do with the system. So understanding what's in there helps you as an EV owner or as somebody who's trying to secure these systems. Again, this is pretty similar to the previous one, a little more simplified, but also shows the internal components here and also a connection to the grid. So the electric grid brings in AC power. The AC power is converted to DC power within the charger. And that DC power is again converted to different levels of DC because different vehicles have different battery pack voltages. So you've got Tesla's at about 400. You've got the Kia EV6 is probably 800. So even once you're at DC, you still need to adjust the voltage. So there's two different stages of power conversion here. One coming from AC to DC, and then DC to DC, and then just straight plugs into the car. The DC connection is established, and it's just like charging any other batteries you've worked with in the past. Obviously, there's communications to the service provider and energy aggregator, the grid itself. Again, just some of the different possibilities when it comes to protocols, communication protocols that are being used. Each of these have different security challenges that you'll have to work with when you get into those. So we talked a little bit about the cybersecurity itself. So we want to talk about why cybersecurity. So we know obviously the safety side of things. And we've got impact to the electric grid. We've got hardware damage, denial of service, data theft, et cetera. So safety itself, pretty self-explanatory. You're dealing with high power, high voltage currents, et cetera. So you want to make sure that the system is protected, designed to be fail-proof in those cases. Definitely, even in the event of cybersecurity attacks on that, you know that the hardware side of things is still protected by a physical mechanism. And impact to the electric grid. So right now, I don't know, we have plenty of chargers coming in, and with several more planning to be installed in the US itself. So when we look at all these as individual points of vulnerability on the system, now you have a grid that is connected to several different electric vehicles that are charging. What if a bad actor got into, let's say, compromise one major vehicle OEM or one major charging provider and is able to turn it on and off at will? What that means is they can mess with the grid in terms of the amount of current being drawn, the amount of power that is being pulled. You can adjust, change it up and down. So that's a pretty bad situation. So you want to make sure that the grid as a whole, even when it's connected to all these different things, you're able to detect and respond behavior that reflects a potential bad actor trying to mess with the system. And obviously there's data theft, which is pretty common in other fields, but you can just extrapolate all of those concerns straight to electric vehicles as well. And I think this, my cyber colleagues tell me this is pretty true, is that with enough time and effort, nearly any controlled system, electrically controlled system, can be accessed or compromised. So it's good for job security purposes, I think, for you guys. You just have to keep staying one step ahead, and you'll always have work to do on that front. So our objectives at the lab itself are determining what we call high consequence events are, the HCEs, and then we prioritize these based on our impact severity and manipulation complexity. So as long as if it is something that's fairly easy to accomplish, like an RFID trigger or something, that we work on that first, and because that is a more serious thing where it is accessible to everyone and also can cause bigger impact on the system itself. So we work on those high impact and low complexity attacks first. And then obviously develop our mitigation strategies and solutions. So going back to our test bed itself, this is what our test bed at INL looks like. Look, I showed you a picture of this charger. So that is where you can plug into the vehicle. We've got our power conversion coming in from the grid. Everything else shown is not what you would see in a commercial or a public charging station. This is all instrumentation that we put in so that we can test out a few things, read these signals, and actually make sure that we are able to detect certain kind of anomalies before they happen, or pretty close to real time when they happen. So we've got power meters, we've got current sensors, and we've got our actual anomaly detection processor over there as well. And with these cables, you can actually put in what we call the current clamp, and you can read the PWM modulation signals to read what communication is going on between the electric vehicle and the charger itself. And this is pretty common, commonly used for debugging, but it could also be, if they're able to crack the encryption on that, you're also able to read sensitive customer data, et cetera. So some of the anomaly detection systems that we worked with your colleagues here, and we've talked again, we've got the charger, sensor data, CCS and CAN communication data. We take the SIS as our little processor that we call a safety instrumented system. Take all of that data, locally process at the site, feeds into the anomaly detection block itself. And beyond that, we also have what's called a physics-based model and also a machine learning trained model. The physics-based model, in short, you are reading all the commands that are going from your charger computer to the physical components on the charger. So this is if I send a command to the charger saying, maintain the cable temperature at whatever 20 C or something. And now I can model that in a physics-based system saying, if my pump is running 50% of the time, this is what the temperature is going to look like, and so on. So what that gives me is, if my pump is running 50% of the time and my temperature is not lining up to what it's expected to be, I know something's wrong. So that's the physics-based modeling system. But that is very intensive in terms of getting the actual model right, because there's a lot of factors. You could be a windy day, you could be a cooler day outside, and now you need to read the ambient temperature and feed that into your equation, and so on. The other one is also our machine learning trained model, where we take all of that data and we know what normal behavior is supposed to look like. And any deviation from that, you can send a flag saying, hey, maybe something's wrong, go take a look, send somebody out to see what's going on. And lastly, all of that goes into, if it's normal, keep going. If it's abnormal, send it into a health monitoring system. Either let the operator know, or reduce power, or stop the charging system. I did outline a few scenarios that we tested with. Again, these were tested in hardware. We worked on these to replicate something like this on our test bed at the Idaho National Lab. So one was a power system manipulation. What that meant was we were able to spoof signals that we sent to the actual controller inside the power conversion stages, the AC to DC, DC to DC. And because of that, now the charger has to react very quickly to regulate power. So it's trying to maintain power at a certain level, but we are turning on and off individual modules, and then has no idea what's going on. So that could potentially cause issues with the vehicle that you're charging, or even just reduce the life of the charger that we're actually exploiting. The next one was a liquid cooling system manipulation. Like I mentioned, we've had liquid cooling systems in the cable itself, so you could send a signal to the coolant pump saying, turn off. But the rest of the system thinks the pump is still running, so it is sending in the full 200, 300 kilowatts through that cable, which is not being cooled. So now you've potentially created a touch hazard. So the cable gets really hot, the connector gets really hot, not really advisable for somebody to go touch it at that high temperatures. And if you can do that enough times, you'll probably melt the cable, cause damage on the connector, and so on. And last thing is also external manipulation of the charging profile. So what a charging profile is it tells the charger what kind of voltage you need to give the car. So the vehicle is always asking for a different current, and because that is it knows the optimal current at which its battery needs to charge at every given state of charge. So if it's at 50%, it's going to ask for a certain amount of current, and so on. So we can mess around with that, change that about. You could change the different steps in which it increases and decreases, and so that can also potentially cause issues there. So I put in some results from some of Victor's work here. I've worked with them. So we've got some physics-based models on the left side. You've got some ResNet autoencoder results on the right side. You can see, so the green line, so this one is what we call its ability to predict the anomaly. So the red highlighted region is where the actual exploit takes place. And you can see when the exploit is in place, you would see how the powers, the voltages, and the currents are changing pretty rapidly. So you can see that the physics-based model is not really able to detect in that first case, where we do have that autoencoder machine learning model coming into place. So you would have the pros and cons of different systems that are able to respond or detect certain kind of errors. So again, you do, as long as it's not cost prohibitive, it is advisable to have multiple systems that are always detecting different sets of data to understand what's normal behavior and what is not looking good in terms of anomaly detection. So beyond that, the Idaho National Lab also works on modeling for grid and transportation simulators. Typically, we've got transportation models on separate tools, and we've got grid models on separate tools like OpenDSS, GridLab, D, et cetera. So Caldera is the EV modeling platform where we bring in both the grid models and the transportation models together. This helps us model things like, where do we want to put the chargers? Where is power available? Where do we need to expand our capacity for providing power? And so on. So that's kind of what Caldera's purpose is. It is to bring together the two different sides, the energy side, the transportation side, and co-simulate them to get high fidelity models for understanding EV impacts on the grid. So yeah, so to be able to do that, what we need is real good data, because your models are only as good as your data is. So if you've got bad models, or if you've got bad data, you could have the best model, but you're still going to be predicting the wrong things. So to get that good quality data, we do testing in lab. So everything that we get in our models or into the modeling tool is actually real data that we picked up from vehicles. So a lot of our work at the Electric Vehicle Infrastructure Lab is to bring in vehicles, test them. We run detailed tests under cold weather, hot weather, all sorts of conditions. Get these, what we call the charging profiles, charging curves. We tell how it's going to behave at every single point in that SOC curve. So, and then once we have that data, this is all high quality, high resolution data. We put that into the modeling, so we're able to get really good models on how these vehicles impact the grid when we plug them in. And we can do the same with the charging side of things, how the chargers work. We can also do the same thing on the battery side of things. So the two pieces that go in, we can get those models for voltages, power factors, efficiency of the chargers, and also our battery state of charges. And a few more images there in the corner from testing at our lab. So, yeah, with that, open it up for questions.
So, I have a couple of questions. So number one, so in your figures, like you had, like, so one place I can see that you said that, or vendor specific protocol, and then you also mentioned like other protocols like OCP or something.
Huh?
So like where exactly, where exactly are the vendor specific protocols being used, and where are the OCP and all these?
Yes.
OCPs?
So typically you would see this being vendor specific are the ones that have not been standardized
Yeah.
yet. So Ford can have its own little network in the back end. They might be using something that is very similar to somebody else. So Tesla could use its own thing. They have their own mobility data that is being sent back to home office, so to speak. So again, our purpose in creating this image was just to understand which ones that we can help secure or help understand the diagnostic side of things. So we can't really mess with the OEM side of things because there's several, but on a cyber perspective, those are all fair game, right? Like all you need to do is compromise one of those and you're good. But on our side, this was more for the reliability effort. So we just look at the ones that are standardized. So you could be charging company A, B, or C, or D. You need to still use OCPP to talk to your own chargers.
So are these encrypted? Like, these encryption?
Yes. Mhm.
Yeah, but what about vendor? Do you have an idea?
My guess is they are like 99% of them, because it would not make sense to not have it, at least a very basic amount of encryption. And I would even say that those are more secure because there's no documentation available. So when you think about the standardized ones you can actually read through what exact layers are available. So you can go through the entire documentation, understand what messages are being sent, and so on. So I would even argue that the vendor-specific ones are more secure in terms of a bad actor having access to the amount of documentation available.
Also, do you know if anything is being done with the slow charging, like any treat with the slow charging in cold weather?
Yes, and so I mean, like I said, there are systems in place, like I talked about, the vehicle battery itself, trying to help send some heat into the battery so it can warm it up before coming to charge. Some of that could be chalked down to user education. So somebody bought an EV, but they're not really familiar with the technology of how it works, right? And again, that will improve over time. It's not like, and we've had gasoline vehicles for a long time, so now folks know all the ins and outs, or at least some of the basic requirements. And similarly, you'll start knowing, people will start understanding that if you're going to go try and get a fast charge, you want to hit that precondition button on your vehicle that tells your battery to warm up, and so on. So, and yeah, it's a little different in the sense that you don't have winter gas and summer gas, so it's not a chemical composition change that's needed. It's more of, hey, you just need to preheat it just a little bit so you're ready to go when you get there. Yeah, I think it's a little bit more of the user behavior change and also just customer education. You put out a little public service announcement saying, hey, don't forget to precondition your car as you're driving this winter, and a few people will learn, and so on. So, and a few other of the dotted lines that I have, like for instance, what is the communication between EV users and EVSE? It's not necessarily a digital communication, but that's just to show that the interaction between a person and a charger is non-standardized, right? Like I might do something that's different from you. Like might plug in first and then press my card or press the button next, and you might do it in a different order, and so on. So that's the purpose of just showing those non-standardized interactions. Yeah. Good.
Other questions? Anyone? This is your unique chance. You have EV expert in front of you.
Okay, I'll ask again.
Oh, go for it.
So, in this figure, can you tell like where would the vendor specific protocol be used?
Uh-huh.
Like in this figure? Like I
Yes.
also have it in another figure, but what about here?
The vendor specific would be this one over here. So the EVSE manufacturer. So the person that's actually making the tower itself is will have a backdoor sort of system to talk to his charger, to understand every single message that's being sent, every single communication link. So they have the ability to turn it off, restart it remotely, in case that's typically what you do, right? Like most problems in engineering, you fix it by turning it on and off. So somebody at the service center is just like, okay, customer called me from this charging station, is telling me that he's not able to get a charge. And sometimes they're more helpful than that, but sometimes all they do is just sit there and reboot it remotely and hope it works. Yep.
You have a question?
Yes, go ahead.
From a security perspective, wouldn't you want to just cut that part out completely and have somebody else do it? Or, I mean, the fact that the manufacturer is involved in all there seems like it.
And again, that depends, because the way it works right now is somebody manufactures the system, but they don't own the operation of that. They're still there, but it's what's called the CSMS, or charging station management system, or someone, it's kind of like when you think about it in a gas station analogy. The maker of the pump might be somebody else, a company that you've never heard of. But the name on the pump is probably Shell or BP or whatever, and they're the operator, right? So this is what you would see as Shell or BP. This is pump manufacturer, Gilbarco or whoever. Those names you typically don't hear of. And usually it's an agreement between these two. So if something's wrong here, the messages go on this person, because this is the person that is making money off of the charging going here. Should they have a vested interest in making sure the charger is running all the time and making sure it is secure, operational, and so on. The reason this link still exists is when they have a problem and they need to debug and they're not able to figure it out, they go talk to this person and say, hey, something's wrong with the charger you supplied to our station, what can you do? And then they dig in, they want to make sure. So it's not, these folks are not actively involved in maintaining the day-to-day operations of that station. So good point, but that's just there as a last resort of debug with the charging station manager. Yes.
So for like unsupervised learning, like the autoencoder, a big deal is defining what normal looks like. So what are you guys doing as far as trying to cover like as many normal situations as possible?
Yeah, and like I mentioned, that goes into sort of the charging models that we develop. So the same tests that we run, as in we plug a charger in, we run it at different conditions. We try to get a wide range of weather-related conditions, like ambient is very low or ambient is very high, ambient temperature, and then how does all these look? So you'd start seeing patterns of, okay, it goes to a certain voltage, it goes to a certain current, then you start seeing the bounds of normal operation, so to speak. But like you mentioned, it's not a foolproof system in terms of there's still going to be normal in the real world, but your system might flag it. So there is a little bit of possibility there for like a false positive.
Even like human factors, like you mentioned, the plug issue, right?
Yes.
It's like, you know that, but I didn't.
Exactly.
So I would unplug it wrong every time, but you didn't plug it correctly.
Yep.
Right, so it would be like a
Mhm.
issue where like that maybe isn't abnormal, but it's not good.
Right. And so that's where the physical part of things come, like it's not just writing the right software to protect it. It's also the design. Like when you design the physical world or the physical component of it in a way that's foolproof. And that just happens over time. And as you learn things, you don't know everything when you first start, but you fail a few times, you learn, and it's a rapidly changing field, right? And we don't realize this because gas stations have been around for hundreds of years. And these electric chargers are pretty new, and which is why you start seeing a lot of issues at the beginning. But over time, you're not going to see that again because that's been taken care of in terms of software and design and so on. So it's an evolving process, and that changes over time. Yeah.
Are these charging models like actually implemented and deployed in like real charging stations?
What do you mean?
Like the charging models, like the INLs,
Mhm.
the EV, are they actually like being utilized like in real world, or are they just?
So the models themselves, so you need to understand, so when I say charging models, so we get the charging data from a real charger, real vehicle. We test them and with our instrumented system, right? You've seen a picture of the test bed with all the sensors and so on. So you can't do that on a real charger outside. But the expectation is that when you take a car, plug it in, it should behave the exact same way outside. And what we're able to do in the lab is actually get data on that. And then we feed that into the modeling tool. And that modeling tool is actually a decision-making tool. So it's not necessarily that the models are deployed, but since it's accurate data and accurate behavior of your car and charger, you're able to make better decisions on where to put chargers, where to improve the grid, and so on. Mhm. Yeah.
What kind of sensing data you have?
So you've got voltages, currents, you've got CAN communication, all the other protocols that are being communicated out in and out. Yes, the physical temperatures.
Their correlation with this kind of data and how it's gonna affect the anomaly detection model because it's based on the data you already collected, right?
Yes. So like we said, we do a little bit on the testing just to get the normal behavior. And in that case, all of our data, the current sensing data, temperature data, all of that is normal for that condition, right? So depending on what kind of data we get, we need to apply different algorithms to that. So in terms of the autoencoder unsupervised learning, we just run our tests. We try and get as many different normal conditions as possible. Again, normal doesn't mean just one. It could have 10 different situations where weather is changing, where there's wind, sunlight, direct sunshine, all of that changes the amount of temperature. So you could have a wide range of temperatures for one normal charge session, right? And so on. So that all of that feeds in. We put that in. Anything beyond that, you start seeing. Or you add in one more variable that says, when the ambient looks like this is the normal operating conditions. So that has been one of our challenges, actually, because the amount of data we can generate is very small. Like it's almost in the low hundreds or tens, just because it's so time intensive to get that charge session started, run individual data point collection, and which is not ideal for machine learning, so to speak, just because it's one instrumented charger. So we're trying to move away from that model of just trying to get our training data from this one. But what is possible is we can get training data from the broader network in general, right? Where you have several hundreds of chargers, and each of them is servicing a lot of vehicles at the same time. But you won't get this level of data. It won't be as detailed because you're not instrumenting chargers in public. It has to be data that you can gather, which is not with non-invasive methods. Invasive being you can instrument it. You can just read maybe the communication that's going from charger to the site manager and some of those digital side of things. So it gets a little harder because you're not able to see everything, but at the same time, you can see lots of stations, but on a very lower level or higher level data. So it's a trade-off. Yeah, go ahead.
So in general, what do you think about the future of these companies like charger companies? Because in the last year, like almost all of them lost their value more than 95%.
Yes. Mm-hmm.
So like, is it a good idea to invest in these?
Yes. Uh-huh.
Lost its value more than 95%. Like
yeah,
it's almost dead.
Mm-hmm.
So what do you think?
Yeah, I can't speak for investing advice, especially not being recorded. But I will say that it's kind of similar to the gas stations, right? So the gas station, the business model is pretty interesting if you look at it. It's actually the convenience store that makes the money because you're not really making all that much profit on the gas itself. The charging stations don't really have that facility right now. they have to make money on the electricity to be profitable, which is pretty hard when there are several charging networks. So I think my personal opinion is that in the future, they will be in close collaboration with existing gas stations, because then the profit model still remains the same, but the gas station pays an additional fee to get a charging station in there. So now they make money from the gas station, so the charging station, the person making the chargers and operating the charging station does not need to worry about just making money on the electricity. They just have to worry about selling it to the gas station, and the gas station still does its usual thing of customer comes in, buys whatever, and the convenience store makes money there. There are a few benefits there in terms of electric vehicle customer stays there a longer time because you need to charge. It takes 10, 15 minutes at least. So you've got a captive audience, right? You've got a customer that's going to stay there longer than your typical gas station customer.
For a
So,
cup of coffee, for example.
yeah, and you probably think, okay, I've got some more time. Let me just, yeah, go eat something. Or so it has to evolve along with that. You know, probably you're going to start people that put in like little arcade games or something. You know, because you're going to stay there just a little longer. And
But that's a good
folks-
question. Why most of the chargers are away from anything
Yeah.
stabilized where you
Yep.
can see it or so? Why are they so isolated?
I think the reason for that is they were not sure whether it's going to take off or not. They just put it in the corner. So if it doesn't work out, we'll just scrap it and take it all out and pretend nothing happened. So I think we're getting to that point. We're starting to see chargers that are having like that giant canopy on top, similar to gas stations. You're seeing chargers with like pull-through sites where you're towing a trailer. You can actually go. Because I was on a road trip once and I saw this older couple. They were driving their Tesla. They had like a little camper on the back, and charger. They had to come, stop, unhook the camper, turn their car around, bring it to the charger, charge, go back, plug it in, hook it up, drive away. So all those sorts of conveniences. Yeah, the early adopters are going to struggle a little bit, and that feedback feeds into future design, how they can make it better, profitable, and so on. So it's a work in progress. Like, yeah, as far as the profitability thing, I think until they start actually getting into collaborations with the gas stations itself, on paper, they can't make enough money with just selling electricity. Yeah.
Any more questions? If not more questions, let's thank Dr.
Yeah.
Varghese.